A bipartite graph is one where there are two sets of nodes, call them the left set and the right set. There are only connections between the left set and the right set, and none from left nodes to left nodes or right nodes to right nodes. It's often not obvious from the edge list or even the graph drawing if a network is bipartite or not, but thankfully there are fast algorithms to test for this. In the drawings, we'll use different shapes and colours for the nodes to keep track of the left and the right sets. Sometimes we're given a bipartite network, but we're more interested in one set than the other. Imagine a network of people connected by hobbies. We might want to know about the connections between the people, and we don't necessarily care how they know each other. We can accomplish this using a technique called projection. In this graph, say we care about connections between the orange circles that are induced by shared connections to a common blue square. One way to project is to add a link between every pair of orange nodes connected via a two-step path through a blue one. When we do this for every neighbour of a blue square, we end up with a clique, a set where every possible connection between the nodes is included. Then we can get rid of the target node and all of its edges. And repeat the process for every node that's being projected. If we have some dangling ends, that is blue squares which don't contribute to any path, we just remove them. What we're left with then is a network of connections between the orange circles. Mathematically, we can express projection like so. This says that the strength of the link in the projected graph, Aij, is just the number of paths in the bipartite network that go from I to j via any intermediate node k. Often, you don't keep track of the weights, and you say that if there is any path, then we add a link in the projected network, regardless of how many ways there is to get from I to j. This is called binary projection, and it's what we've been doing in the animations. For real networks which arise from data, you often want something more subtle. Real networks often have a small number of nodes with a huge number of edges attached to them, which are called hubs. Since these hubs contribute to so many paths, we often want to downweight them. We do this by dividing by the projected node's degree, which is called hyperbolic projection. Sometimes even that's not enough. When we divide by the square of this, it's called unary weighting. In the animations that follow, we use binary projection for all the networks, which are quite symmetrical and don't have any hubs, except for the Southern Women network, which has many. For this one, we use a unary projection.